Hello and welcome. In this video, we're going to be sketching another rational function. However, this one is a little bit different. So let's see how we can sketch it. So first of all, let me give you what is the function. So the function looks something like this. It's f of x equals to 2x squared plus 10x plus 12 over x squared plus 3x plus 2. That is the function that we have over here. So let's go on with our steps in order to successfully sketch the function. So the first step is finding the domain of the function. So let's start by doing that. However, first let me try to factorize if this is factorizable. So first I can see that I can take a 2 out of the numerator. So this is going to be x squared plus 5x plus 6. The reason I did that is then that this quadratic will have an a of 1, okay, which is going to make my life easier when I'm trying to factorize. I could factorize it like this as well, and I've done a full playlist on quadratics. Go check it on the right top hand corner. However, I just want to get the easy way and put it in this form so factorization is even easier. So it's gonna look like factorization of this one. So let's actually factorize the denominator. So this sign is a plus. I will need 2 factors of this number that add up to the middle number, and I can see that 2 times 1 equals 2, so they're factors of 2, and 2 plus 1 is 3, so my answers are 2 and 1. So I will do my 2 brackets over here. I'll do an x, I'll put 2, I'll put 1, and then again, since this is a plus, they both take whatever the middle sign is. So in this case, the middle sign is positive, so my 2 brackets are gonna take the positive sign. Again, let's do the same thing, but for the numerator. Again, this is positive, 2 factors of 6 that add up to 5. I know that they are 2 and 3. So this is going to be written as 2 into, let's open 2 brackets, x and x. I know that 2 and 3. Again, this is plus, so both of them will copy whatever the middle sign is. Middle sign in this case is plus, so I'm going to have a plus and a plus over my denominator, which is x plus 2 over x plus 1. Straight away, I can see that there is a common factor, the x plus 2 and the x plus 2, and they will cancel out. So I will need to put this in my mind when I reach into the third step, where I figure out, do I have any holes or no? So for now, let's think about the domain. So first, domain. Domain is basically anything that x can be without any restrictions. So in this function over here, I have a restriction. I have a restriction that tells me that my denominator cannot equal 0. So what 2 values will make the denominator 0? To find them, I can equate the whole denominator to 0. So I will equate x plus 2 into x plus 1 equals 0. And then from here, I can deduce that either x plus 2 equals 0, which will give me x equals minus 2, or x plus 1 equals 0, which will give me x equals minus 1. So my domain is basically anything except those 2 values. So x cannot be equal minus 2, and x cannot be equal to minus 1. Why? Because if I substitute minus 1 over here, this whole thing is going to be 0. So this whole thing is going to be 0. So the whole function is going to be undefined, and same goes for x equals to minus 2. So let's erase this. Okay, so this is the domain step done. Let's now take a look at the x and y intercepts. So over here, let's think about the x intercept. So the x intercepts means that I will set my y to 0. So my y, which is my f of x, is going to equal 0. So I'll basically take this whole thing, copy it, let's put it over here, and then I will equate it to 0 and try and solve. So straight away, I know that if the numerator is 0, then this whole thing is going to be 0. So let's equate the numerator to 0. So what I can do, I can take the numerator, copy it again, I'll put it here, and I'll equate it to 0. I can divide both sides by 2. So this 2 is going to cancel, and we're going to have x plus 2 into x plus 3 equals 0. Again, I will have two answers. The first one, x equals minus 2 and x equals minus 3. So these are my x-intercepts. All right, is this correct? If you tell me this is my x-intercept, I will tell you are right. However, this one, I can see that this is outside of my domain because x cannot be equal to minus 2. So this one is not going to be an x-intercept. So I will not take it as an answer. So the answers for the x-intercept, let's write it neatly, is just going to be x equals minus 3. Okay, now y-intercept is a little bit easier. So y-intercept is just basically me setting my x to 0. So over here, if I set my x to 0, I will have 2 into 0 plus 2 is 2 times 0 plus 3 is 3 over 0 plus 2 is 2 into 0 plus 1 is 1, so times 1. So over here, this 2 and this 2 can cancel. 2 times 3 over 1 is basically 6. So y is going to equal 6. That is going to be my y-intercept, and this is my x-intercept over here. So the x-intercept and y-intercept steps are done. So let's check what is the third step. Third step is saying determining the vertical asymptotes and holes and the zeros. We already found the zeros in the previous step. Zeros are the x-intercepts. So let's try and find the vertical asymptotes and holes. So for vertical asymptotes, we know that vertical asymptotes occur at values that will cause the denominator to become zeros. So basically, whenever there is an x value that will cause the denominator to become 0, this x value is called a discontinuity. We have a discontinuity. Discontinuity can be two types, either a vertical asymptote or a hole. So first, let's get our two discontinuities. So what two values will make the denominator 0? We already figured them out. It's x equals minus 2 and x equals minus 1 over here. But I can see that for this discontinuity, when x is minus 2, I can see that this can be cancelled, or this is shared, or it's a common factor between the numerator and the denominator. And from the previous video, which I'm going to leave a link to it on the top right hand corner, this basically means that x equals minus 2 is no longer going to be a vertical asymptote. However, it's going to be something called a hole in my function. And x minus 1 is just normal. I don't have any factor that cancels with x plus 1. So x plus 1 is a discontinuity and it's a vertical asymptote. So these are my answers over here. The fourth step is to find any horizontal asymptotes. So for horizontal asymptotes, let me take my original function, which was this one, and let's see how can I find the horizontal asymptote. So horizontal asymptote, what I do is I take every single term and I divide it by the highest x degree term in the denominator. So what's the term with the highest degree of x in the denominator? Is basically x squared. So I'm going to divide everything by x squared. So this is going to equal, and I'm going to take the limit as x approaches infinity of everything divided by x squared. So this is going to be 2x squared over x squared plus 10x over x squared plus 12 over x squared over x squared over x squared plus 3x over x squared plus 2 over x squared. So over here, let me think what each term is going to be. So again, limit as x approaches infinity of 2x squared over x squared is basically 2 plus 10x over x squared is basically 10 over x, because one of the x's is going to cancel. This one is going to be just 12 over x squared, nothing I can do here. X squared over x squared is 1, plus 3x over x squared is 3 over x, plus 2 over x. So this is what I have over here. Now let me apply my limit. When x approaches infinity, I know that if there is something that is very large, or something that's over infinity, you can try do anything over a very big number, like anything over 1 billion is going to give you a very, very small value. So the limit, as the denominator reaches infinity, the limit is going to equal 0. So anything over infinity is going to be 0. So this whole term is going to be 0 when x approaches infinity. This whole term is going to approach 0 when x approaches infinity. This as well, and this 2. So my limit is going to give me an answer which is going to be 2 over 1, or basically 2. So my horizontal asymptote occurs at y equals 2. Now I found my horizontal asymptote. Let's see what is the next step. The next step is finding f dash of x, finding all critical points and determine intervals where f of x is increasing or decreasing. Okay, so let's differentiate this function. So part 5, if this is f of x, let's get f dash of x. I can see that this is a rational function, so I can use the quotient rule in differentiation to do that. Okay, please go check my differentiation playlist on the top right hand corner. It's super, super useful. So it goes like this. It's the differentiation of the numerator. So differentiating 2x squared plus 10x plus 12 is going to give me 4x plus 10. So the differentiation of the numerator, multiply the denominator, x squared plus 3x plus 2. And then minus the differentiation of the denominator, which is going to be differentiation of x squared is 2x, differentiation of 3x is 3. So differentiation of the denominator, which is this term, multiplying the numerator, which is 2x squared plus 10x plus 12, all of this over the denominator squared. So it's going to be x squared plus 3x plus 2 all squared. So over here, I can multiply everything out. So let me multiply everything. So I'll have 4x times x squared. That's going to be 4x cubed. 4x times 3x is basically plus 12x squared. 4x times 2 is plus 8x. Now I'll start multiplying the 10. So 10 times x squared is basically 10x squared. 10 times 3x is 30x. And 10 times 2 is basically 20 over here. And then I'll have, okay, let me multiply this minus inside over here. So this is going to be plus, and this is going to be minus and minus. So I'm going to have minus 2x times 2x squared is going to be minus 4x cubed. Minus 2x times 10x is minus 20x squared. Minus 2x times 12 is minus 24x. Minus 3 times 2x squared is minus 6x squared. Minus 3 times 10x is minus 30x. Minus 3 times 12 is minus 36. That's a very long numerator, but we will simplify it over here. The denominator, I'm going to write it actually in the differentiator. Actually, no, I'm just going to copy it. So x squared plus 3x plus 2 all squared. So now, let's take the cube terms first. So I have a 4x cubed. I have a minus 4x cubed. Do I have anything else? No. So 4x cubed minus 4x cubed, they basically cancel out. Now, let's take the x squared term. So I have a 12x squared plus 10x squared. That is 22x squared. 22x squared minus 20x squared is 2x squared. 2x squared minus 6 is minus 4x squared. Then let's take the x terms. So I'll have 8x plus 30x, that's 38x. 38 minus 24, that is going to be 14x. And then I have a 14x minus 30x is going to give me a minus 16x. And let's do the terms without any x's. So I just have 20 and I have minus 36. So 20 minus 36 is minus 16. And over here I have x squared plus 3x plus 2 all squared. So this is my f dash of x. my critical points or my stationary points occur when f dash of x equals 0. So if I equate this to 0, which means that I'm equating the whole thing to 0, I can see that let me actually rewrite this as, okay, let's do factorizing. Let's factorize the whole thing. Before equating it to 0, let's simplify a little bit. So what I'll have is, let me take a minus 4 out over here. So I'll be left with x squared minus 4x squared divide minus 4 is x squared. Minus 16x divide minus 4 is plus 4x. Then minus 16 divide minus 4 is plus 4. And then over here, I have a big bracket all squared. And let me factorize the what's inside. So this is going to be x and x. We said two factors of 2 that add up to 3, so 2 and 1, so 2 and 1, they both copy the middle sign, so plus and plus. If I distribute this squared inside, so this is going to be squared and this is going to be squared. So over here, this is going to be minus 4 into, let's factorize this again. So 2 factors of 4 that add up to 4, so there are 2 and 2. So I'll do 2 brackets, x and x, 2 and 2, they both copy the middle sign. So this is what I have over here. So x plus 2 squared into x plus 1 squared. So this is my first derivative over here. So if I equate it to 0, you tell me, okay, equating it to 0 means equating the numerator to 0. So clearly when x equals minus 2, the numerator is going to be 0. I tell you yes, however, we have a problem that x equals minus 2 is not in our domain. It's not in our domain, okay? And also, you can see that simplifying, it's actually x plus 2 and x plus 2 are going to cancel out with the x plus 2 squared in the bottom. So this is going to be similar to minus 4 over x plus 1 all squared. Equating that to 0, there is no such value of x that will make this 0. This means that I don't have any values of x that will cause my first derivative to become 0. It means that I don't have any stationary points or turning points. Okay, so what we can do now is we can use our first derivative for something useful. We can determine the parts where the function is increasing or decreasing. So let's draw a number line and let's put on our number line our critical points. So our critical points, did we find any critical points from equating the first derivative to 0? No, we didn't find any stationary points. So our critical points are just going to be the points that are not in the domain. So x equals minus 2 and x equals minus 1. So let's say this is x equals minus 2. This is x equals minus 1. And we are testing f dash of x. So what I'm doing is basically I'm taking a value from this interval and substituting it into f dash of x and seeing what is my answer. Is it going to be a negative answer or a positive answer? So let's choose an x in this interval. I can choose x equals minus 3. That's the tester. So over here, I'm going to substitute 3 into f dash of x. And when I do that, it's going to be negative 4 times 3 squared minus 16 times 3 minus 16 over minus 3 squared plus 3 into minus 3 plus 2 all squared. This is going to give me a negative answer. So my f dash of x is negative in this interval, meaning that my function is decreasing in this interval. Over here, I'm going to repeat the same thing. Let's choose a point that's within this interval. Between negative 1 and negative 2 is negative 1.5. When I put negative 1.5 over in the f dash of x, it's also going to give me a negative answer. So my function here is decreasing. Since I don't have any stationary points, I would not expect the function to be decreasing and then increasing again, because when we have a change in decreasing, so and then it starts to increase, that means that we have a critical point. However, we said that there are no stationary points, so probably the graph, or certainly the graph, is going to always be increasing or always be decreasing, and in this case it looks like it's always decreasing. Just to be sure, let's try one more point over here. A point that's to the right of -1 is basically x equals 0. That's an easy point. So this is going to be -16 over 2 squared, so -16 over 4. So negative over positive is a negative value as well, so it's decreasing. So now I know that my function is always decreasing in all of my domain. So now let's use all these information to try and draw our function over here. So let's do, yeah. Okay, so first in drawing, the first thing you should do is always draw your your vertical asymptote and your horizontal asymptote. So over here we have a vertical asymptote at x equals -1. So let's say this is x equals -1. Let's draw a vertical asymptote over here. And our horizontal asymptote was at y equals 2. So let's draw, let's say y equals 2 is over here. So when sketching, you don't need to be accurate with your scale. Okay, so these are our two asymptotes. Next, we put in the x-intercepts and the y-intercepts. So the x-intercept, we found it at x equals -3. So this is x equals -3. Our y-intercept was at y equals 6. So it's probably very high up. Let's say it's over here. Okay, let's actually put it like over here just for ease of visualization. So 2, 4, 6. Yes, it's actually here. Okay. Other than that, what do we have? We have finished our x-intercept and our y-intercept. Now, what else do we have? We need to take care that we have a hole over here. So at x equals -2. So over here, we have a hole. So we need to take care about this point over here. We will have a hole. So I have two options of my graph. Either drawing it like this and like this, or like this, or like that, or how do I know what is my graph looking like? This is gonna help me. What's gonna help me is the first derivative. Okay, let's name them. This is x equals -1. This is -2. This is -3. This is y equals 2. So let's take a look at the first derivative. So the first derivative tells me that it's always decreasing. Okay, so the interval from to the left of x equals -2 is decreasing. So this area is all decreasing, right? So this area is decreasing. So how would the function look like if it's decreasing? Is it going to look like this, or is it going to look like that? 100% is going to look like this shape, because this function is actually increasing. So that's how my first derivative helped me in drawing or determining the shape of my function. So my function is going to look something like this, and I know that there is a hole over here, so I need to take care of it and then continue my function over here. Okay, so this is my function on this side, and on the other side it's always decreasing as well. So to the right over here in this area, I have two options. Either it's going to be drawn like this or like that. Which option is it decreasing in? Yeah, actually over here we had something. We know that our x-intercept is at -3, so we need to touch our x-axis at -3. So it's gonna look something like this, and the hole is gonna be here. Then it's gonna continue over this way. Okay, so this is going to be the left part of our function. Okay, and then the right part, again, we have our y-intercept over here. That even tells me that my function is going to look something like this. And also my first derivative says that in this area, my function is decreasing, so 100% it should look something like this. So this is a decreasing graph. The other option would be an increasing graph, which is not correct. Decreasing means that the slope is negative. Like over here, when you take tangents at any point in this interval, the slope is always going to be negative. And over here, it's the same thing. When we take the slope at any point, the slope is going to be negative. That tells me that the graph is decreasing, or this is how to show that the graph is decreasing. So this is how to plot this function. We don't need to find the f double dash of x. This is more than enough for this function. No inflection points. This is just a rational function. The problems in where we actually will use a lot the f dash of x and the f double dash of x is actually when we're drawing polynomial functions, and I'll be doing that in the next video. So please don't forget to subscribe so you don't miss out anything. Leave a like, comment down below if you have any questions. Hope you found it helpful. Thank you for watching and have a nice day.